Good afternoon, everyone. I welcome you to the fourth problem solving session of NPTEL tutorial Combinatorics. So, from last few weeks, the attendance is dropping. I urge you, like if you're watching these recorded videos on YouTube, I urge you to attend the live. If you are enrolled in an NPTEL Combinatorics course, I urge you to attend the online classes. And if you have any reviews about these sessions, or if you want me to solve particular problems that you want to be discussed in that you would like to be discussed in the problem solving session, you can post them in forum also. So we NPTEL team will very much like if you'll attend the live sessions and get benefit from it. So let me start the session. So today we will be discussing. So today's plan was to discuss the some problems from NPTEL week 4 and also the assignment 2. So if students would have joined and if anyone has issues in the assignment 2, we would have discussed that. So first we'll discuss the first we'll recall the topics that were covered in week 4. So the first was the principle of inclusion exclusion. So basically it says how to, so if you have some sets, if you are supposed to count the counts at some elements in a set and those sets are not disjoint, they may have some intersection. So principle of inclusion exclusion gives you a way to calculate that. So basically it says that if you want to calculate, if you have n sets which need not be disjoint, the order of the union of n sets is given by this. So first you add, first you basically take alternate sums and you keep on increasing the number of indices. So this is how you calculate principle of like how you, and this you can see is a generalization for n equal to 2. For n equal to 2, from the Venn diagram we can see that if we have two sets A, B, and if we want to calculate A union B, it is just order A. So if this is A, this is B, and this is C. So A union B is A plus B plus C. And you see that this A plus B is basically order A, and C can be written as B plus C minus, it can be written as C can be written as B plus C minus B, and B plus C is just order B, and B is A intersection B. So you see, this is the generalization of calculating the order of two sets which need not be disjoint. Then secondly, new concept was introduced, that is of partial order set. So partial order set is a set S which has a partial order relation. And partial order relation, it is motivated from a relation less than equal to. You see, so this relation has to satisfy three property. First property is reflexivity, that so if we call this relation less than equal to, so x should be less than equal to x for all x belongs to x. Then we have a anti-symmetry, that x is less than equal to y. If x is less than equal to y and y is less than equal to x, then x is equal to y. And then we have transitivity, that is if x is less than equal to y and y is less than equal to z, then x is also less than equal to z. So we see this is this is what is called a partial order set, or we also called it poset. So as I said, it is a the partial order is motivated from less than equal to relation. So if you want to look at the examples of 2, you can look at any set of real numbers. First example will be real numbers or any subset, natural numbers, whole numbers with the less than equal to relation. And moreover, you can see greater than equal to is also a partial order. This will also be a partial order. What and other non-trivial examples that we studied were First one was, it was on natural numbers also only, and the relation was divide. So basically, A divides, A is less than equal to B if and only if A divides B. And we saw that this is a partial order. And another example was, we could take Bn, which was just set of first n natural numbers, and we can take a partial order to be containment. This was a example. And now then we had a new notion of a rank of a poset. So by a rank n poset, we mean a poset S whose all maximal chains are of length n. So first of all, what is a chain? Chain is a subset S of some P, where P is a poset, such that every element is comparable. Every pair of elements are comparable. That is, AB belongs to S implies A is less than equal to B or B is less than equal to A. And we also had some, we also have Deichen diagrams to represent them, and we saw that chain looked like this. Because every element is comparable, it will look like something like this. And a poset S will be called a rank n poset if we take every maximal chain and it is of length n, then it is a rank n poset. So this was the topics that were covered. Now let's solve some problems. So our first problem is that we have to find the number of 5 tuples S1, S2, S3, S4, S5, where each of these Si is a subset of 5, square bracket 5, which is the set of first 5 natural numbers, which is 1, 2, 3, 4, 5. So you have to find the number of 5 tuples, that is S1, S cross S2 cross S5. You have to find such S5 sets where each of these Si is contained in 5. And first part is, it should satisfy that union of Si is equal to 5, which is union of Si is equal to 1, 2, 3, 4, 5. Okay. Okay. Sorry. Yeah. Now, okay. So first of all, if we are saying union Si, I going from 1 to 5 is 5. What do we mean by that? That if we have X which is belonging to 5, then X should belong to at least one of Si, isn't it? Because if union of all these sets is the whole set, which is 5, so for each X, that is 1, 2, 3, 4, 5, it should belong to at least one of Si. So suppose I take my X to be 1. So what are the possible options for X? X, that is, X belongs to exactly one Si, X belongs to exactly 2 Si, or X belongs to X belongs to all Si. So X belongs to all Si, that is 5 Si. So we go from 1 to 5. So we have these 5 cases. Now we see, so if we take our Tx to be all those I such that X belongs to Si. So what, first of all, if Si has no conditions, if Si has no condition, that is we don't have this condition that union Si, no conditions, no restrictions, that is we don't have this condition union Si I going from 1 to 5 is 5, then what are the possibilities of Tx? It is basically X can either belongs to 1, S1, X can belongs to S2. So you can see it is basic any possibilities for Tx will be that Tx will be a subset of 1 to 5. Okay, so somebody joined. So we were discussing this question. So we are discussing this question, that is we have to find the number of 5 tuples S1 till S5 contained in 5 cross 5 cross 5 where round square bracket 5 is the set of first 5 natural numbers, which 1 2 3 4 5, and we have to find the number of possibilities, number of 5 tuples Si where each of these Si is a subset of 5, and these Si's are satisfying this first condition that A union Si is equal to 5. So now if you want to solve this question, union Si is the complete set 5 if and only if for any X in this, that is X should belongs to at least one of Si, then only we can say that union Si is equal to 5. So what are the possibilities for X? Like, so if we have some tuple S1 till S5 which is satisfying this condition, S1 S5 which is satisfying A, what are the possibilities of X? X can, it can be, we have that X should belongs to at least one of Si. So the possibility is that X is in exactly one of X is in exactly one of these Si. Second is X is in exactly two of Si's, and so on. So if now we see, so now I am creating another set, say Tx, where X belongs to, for each X in 5, I am creating Tx, which is basically recording all the indices I where X can go to. So now if I know, if I in this first case, the possible option for X, if X was belonging to exactly one Si, then my Tx was that I, and if X was belonging to exactly two Si's, then my Tx was those two indices Ij where X was belonging to. And now our condition is that union of all these Si's, S1, S2, S5, this should be 5. Therefore, we know that this X should belongs to at least one of the Si. So what are the possibilities of Tx? First of all, from this we see that Tx should be a subset of 1 to 5. That is, Tx is recording the indices where X is going to. Now what are the possible, which all subsets Tx can be? Can you tell?
Ma'am, can you repeat once again, ma'am? I don't understand, ma'am.
Yes, okay, sure. So did you understand the question? What we are trying to find? Hello?
Please wait, ma'am. I will see, ma'am.
Yeah, okay, yeah. So we are we are trying to find a 5 tuples of set. So each of these S1, S2, S3, S4, S5 is a set. It is each of these Si is a subset of 5. Okay. Now we have to find all those 5 tuples S1 till S5 such that union of Si is 5. So basically, we have to find all the possible combinations, S, all the possible subsets S1, S2, S, all these 5 tuples such that union Si is equal to 5. So is the question clear?
Yes, ma'am.
Okay. Now, if we so now what if we have to find the possible tuples? So what we are doing is, so we have this condition union Si is equal to 5. Therefore, for any x in 5, since union of all these union of S1 to S5 is 5, so this each x should belongs to at least one of the Si, right? Because
Yes, ma'am.
so now we are looking at what are the possibilities for x to belong, what all possibilities are there. So so if so since x should belongs to at least one of Si, so we have that either x can belong to exactly one Si, either or x can belong to exactly two Si's, or go on like this: two Si, three Si, four Si, and five Si's, because we have five sets, type tuple of five. Now we are creating using this another set Tx, which is basically recording the indices I where x can belongs to. Okay.
Yes, ma'am.
Tx is basically all those indices I where x is going. So now we want that x should belongs to at least one of Si. So we know that this Tx, since we have 5 options, 1 2 3 4 5, this Tx will be a subset of 1 to 5, right?
Ma'am.
Because we have 5 indices. And now we want, so what are the possibilities? What are the possibilities of Tx if we want that x should belongs to at least one Si? X belongs to at least one Si. So that means X, there should be at least one index in the set, right?
Yes, ma'am.
So what are the possibilities for Tx?
5 possibilities, ma'am.
Yes, a 5 possible. It can, but if it is belonging to exactly one Si, then it has 5 possibilities. But we are saying that union Si is equal to 5, so it can belongs to one Si, or it can also belongs to multiple Si's, as long as it is belonging to at least one Si. So what are the possibilities of Tx? So you see that Tx will be a non-empty set. Because so see, if we have all these possible options for Si, so if x belongs to exactly one Si, then we see that Tx will be equal to I, right? Hello. Yes.
Uh, yes, ma'am. How can we tell Tx will be a non-empty set, ma'am?
Yes. So see, yes. So we saw earlier that x belongs to. We want that x should belongs to at least one Si. So what are the at least one Si? And there are five Si. So basically, so what are the options? It is belonging to exactly one Si, exactly one Si, exactly two Si, and exactly five Si. So if it is belonging to exactly one Si, then what is our Tx?
1, ma'am.
Yeah, Tx is basically Tx is basically
I.
that index. Yeah. Now, if it is belonging to exactly two Si, say SI, then what is our Tx?
I, comma, j.
Yeah. And if it is belonging to three Si's, say IJK, then what is our Tx?
IJK, ma'am.
Yeah.
It will increasing up to 5 variables, ma'am.
Yeah. So see, so in all these cases, so we have that. So we are calculating one. So all these subsets are included except the empty set, right? We want that x should belongs to at least one Si. and Tx is recording the indices where x is going to.
What, ma'am?
Yeah,
I didn't get, ma'am. Last point.
yeah. So I am saying that what is our Tx? What is our Tx doing? So if my x is 1, so first we are calculating these 5 tuples S1 till S5. So if my x is 1, what is my T1 is? T1 is,
T1,
yeah,
1, ma'am.
yeah, okay, yes. So, so first of all, S1 cross S2 cross S5. These each SI is a subset of 5 cross 5. Now I'm giving you this like one element of this set. Like if we are considering all 5 tuple, this is one possibility. 1, 1 comma 2, 1 comma 3, 3 comma 4, and 4 comma 5. Suppose this is 1. So first of all, do you see like this belongs to, this is a 5 tuple that we are required, right? So here what is T1? In this example, what is T1?
1, ma'am.
T1, okay, so this is my S1, this is my S2, this is my S3, this is my S4, and this is my S5. So T1 is basically all
Yes.
those I such that one belongs to Si. So what is T1? You're right, T1, one should be there, but what else should be there? So this is my S1, this is S2, this is S3, this is S4, and this is S5. So T1, you have to count, or you have to take note of all those index. Index is the lower step with where one is going to. So one is in S1, one is in S2, and one is in S3, right?
Ah, yes, ma'am.
So T1 should be, it should be
Ah,
1, 2, and
2
3.
and 3.
Okay?
Yes, ma'am.
Yeah. So hence now, like once we know this, then we can see that we want union of Si to be 5. Therefore, we see, so therefore our Tx should be non-empty for all x belonging to 1 to 5. Because if we have that union Si is 5, that means 5 is 1, 2 till 5. So all these, this 1, this 2, this 3, this 4, this 5. So if x is 1, this should belongs to at least one of these Si. So therefore Tx is non-empty.
Okay, ma'am.
Okay. And so now we have x can take 1, 2, 3, 4, 5. So what are the, so if your 5 is this, what are the number of non-empty subsets of 5?
5, ma'am.
Yes, you can, so you can check that non-empty subsets of 5 will be 2 raised to the power 5 minus 1. So we are talking about the order of all the possible subsets. All the possible subsets are 2 raised to the, number of all the possible subsets is 2 raised to the power 5, and the non-empty one is 1. Hello? Okay?
Ah, okay,
So
ma'am.
this was done in week 1, that like the non-empty subsets of non,
Yes,
sorry,
ma'am. Yes, ma'am. I understood, ma'am.
yes, okay, okay, sure. So this was our first part. Now our second question is, now second part is, again you have, again we are required to find a 5 tuple which is a subset of 5 cross 5 cross 5 such that S1 is contained in S2, S2 is contained in S3. So we have this containment. Okay?
Okay, ma'am.
Yeah. So what kind of subsets are, so what kind of tuples are we required to find that this is the condition? Fine. So now can you say, like, if X, suppose if X belongs to Si, so suppose X belongs to S1, then what can we say if we have this condition? If X is in S1 and since S1 is contained in S2, we can say that X will belongs to S2. Is this fine? Right?
Yes, ma'am.
X belongs to S2, S3, S4
S4.
and S5. Yeah?
Yes, ma'am.
So if we are, and so basically we can say that if X belongs to Si, then X will belongs to Si plus 1 till S5, because we have a containment like this, right?
Yes, ma'am.
So now we are required to find the find a collection of subset of 5 which is satisfying this property. So we can see if let n x be the least number where x x s nx be the least number where x belongs to snx. So basically we have this tuple for each x equal to 1 to 5. We are we are finding nx, which is n1, n2, n3, n5, which we are saying that ni is the number where x first belongs to. Okay? Ni is the
Okay, ma'am.
number where x first belongs to, because we know if we can, because if we have to find this type of containment. So we know if we know where the least number, so if we have that 1 2 3 4 5 and we have our n1s, this is x, and if our nx is basically some random numbers, say if I'm saying it is 1 2 2 2 2, so what I am saying that I am giving the least I am giving the first subset where x is going to. So this kind of tuple will give me this this number nx will give me these type of subset s1 till s5, and here so s1 will be so this is nx is the number which is going to this. So what will be s1? So if x is 1, nx is 1, that means 1 belongs to s1 for the first time, 2 belongs to s2 for the first time, 3 belongs to s2 for the first time. So we can see that s1 is just 1, and s2 is all the s2 will be all those, it will be consisting of the number, since s1 is in s1 and s1 is contained in s2, it will contain 1, and also
2.
those numbers which are appearing for the first time in s2, which are 2 3 4 5. Is this clear?
Yes, ma'am.
And what will be s3 then?
1, 1, 3, ma'am.
Yes, what will be s3?
3,
3. Yeah, s3 will be 1 2 3 4
3,
5,
4, 5.
because see, so and so we are nx is, so this is the least number, this is the least number, or this is the number where x is appearing for the first time, and we know that if x appears in a smaller si, Then since we have this containment condition, x will also belongs to the later Si. And in your S2, we have all the x's. So in the later S3, S4, S5 also we'll have all the x's.
Ma'am, this part I don't understand, ma'am. Let nx be the least number where x belongs to snx.
Yeah. Yeah. So
Yes.
yeah. So I'm saying N1 is the N1 is basically the set. N1 is, if N1 is the that x appears for first time in Sn1. N2 is 1 appears, sorry, N1. N2 is 2 appears for first time in Sn2. Okay. So now if I have 1, 2, 3, 4, 5. This is my x. And now my nx, which is the n, my n1 is equal to, say, now if I'm saying my n1 is equal to, say, 2, 3, 2, 3, 2. Okay. So this is nx. So basically n1 is 2, n2 is 3, n3 is 2, n4 is 3, and n5 is 2. Okay.
I
So
didn't
what,
get you, ma'am.
yeah, so what do we mean by n1? N1 is equal to 2 means that 1 appears in S2 for the first time. And what do we mean by that? That 1 is in S2, S3, S4, and S5. Okay. And if my N3 is, in this case, N3 is also, so N2 is 3. So that means 2 appears in S3 for first time. Two appears in S3 for first time. Therefore that means 2 is in S3, S4, and S5. So this number nx is deciding where x is going to first time. And if x, and it is, so whatever this number is, x is going into that and all the sets after that. Now is it clear? So if your n4 is 3, what do we mean by that?
S4, S5, ma'am. 3 containing S4 and S5.
Yes, very good. That is 3 belongs to S4 and S5. So now you get it, right? So,
Yes, ma'am.
so now, yeah. Now if now now we are, so now it is, if we have to find S1 to S2, S3 tuple like this, so it is sufficient to give, these number n1 till n5, right? Because if we know n1, if we know n2, and if we know n3, if we know n4 and n5, we know where each of these one are appearing for the first time. And if we have these, we can construct this tuple in the following manner like we constructed above. So what are the possible options for each ni? What are the possible options for each ni?
I, ma'am.
Yeah. So n1. So suppose n1. What are the possible options for n1?
1, ma'am.
So n1 is counting where 1 is going for the first time. So see here, so how you are saying 1. Here you see we could take n1 is equal to 2, and in the previous example we also, in the previous case we took n1 equal to 1. So what are the possibilities for n1? N1 is counting. N1 is basically
1, 2, 3, 4.
1, 2, 3, 4, 5. These are the possibility, right? And 0 also. It can be there. It can be that 0, not 0. 6, kind of 6 also. That means it is a possibility that one is not belonging to any of these sets. That is also a possibility. So we see that N1 has 6 possibilities. N1 has 6 possibilities. And what are they? That one belongs to S1 and S5. This is the first possibility, that one belongs to all the SIs. Second possibility is one belongs to S2 till S5, right? Other possibility is that it belongs to S3, S4 and S5. This is the third possibility. Fourth possibility is it belongs to S4 and S5. And fifth possibility is that it belongs to just S5. And sixth possibility is that it does not belong to any of the SI. Do you understand how we are getting these 6 possibilities?
Yes, ma'am. Ma'am.
Huh?
Yes, ma'am.
Okay. S5. So each has 6 possibilities. So one has 6 possibilities. And similarly, for all these elements 1, 2, 3, 4, 5, all these will have 6 times 6, 6, 6 possibilities. So we see the answer will be 6 raised to the power 5. Is this fine?
Yes, ma'am.
Okay. Okay. So first we'll do this question. So you have studied compositions, right? So we have to find the number of integer solutions for x1 plus x2 plus x3 plus x4 is equal to 18. And we have these conditions on x1, x2, x3 and x4. Suppose if we had no conditions on these xi's, do we know what are the possible integer solutions? Okay. Yeah. So find number of integer solutions for this. So so we have this, that if x1 plus x2 plus x3 plus x4 is equal to 18, and suppose we have unlimited choices, that xi is greater than equal to 0. That is the only condition we are required. So this problem is equivalent to saying that we have 18 laddus and 4 students. And this problem is equivalent to saying that we want to find number of ways to distribute 18 laddus among 4 students. So how can we do that? First of all, we keep all these 18 laddus till this. Now we want to distribute these 18 laddus. So laddus are whole. So we want to distribute these 18 laddus among 4 students. So what do? We start on this, and there are no conditions. So we start on distributing the laddus, and we put a line when the distribution end for that student. So Suppose we give 3 laddu to first student, we add a line here, then we another student takes 2 laddu, so we add a line here, and then the next student takes all the laddus, so we take a line there, and for the fourth student there are no laddus left, so we have to put a line here only, so there are no other possibility. So we have these 18 laddus and we want to distribute them amongst students, so we can see, so we the number of places where we can put the line are, so we see,
Solutions, ma'am.
yes, hello, yeah, hello,
Yes, ma'am.
yes,
Tell me, ma'am.
yes. So what are the number of ways to distribute these 18 laddus among 4 students?
Mm. Maybe 4, 4, 4, 6.
Yeah, that is one possibility. So what we are, so suppose, see, let's do a small case. Suppose we have 5, suppose we have 5 laddus.
Yes, ma'am. I have a doubt, ma'am.
How? Yeah,
But here,
yes,
range is also given, ma'am.
yes, yeah. So yes, range is also given. Yes, I know that. So I'm saying, like, if there was no range, if no range is given, then what will be the answer? First, what will be the answer if no range is given? So this is so basically you can like say, so this is basically a case of composition, and it will be uh, so we composition, and so if no range is given, then we know our answer is 18
Yes,
plus
ma'am.
3, choose 3, right? When no range is given, this is the answer, right?
Yes, ma'am.
Are you clear why this is the answer?
Yes, ma'am.
Okay, but now we have that, now we have these range, now we have these ranges are also given, that 1 x1 is less than equal to 5, minus 2 is less than equal to x2. Now we have these we have this ranges. So what do we do? And we have to find x1 plus x2 plus x3 plus x4 is equal to 18. Possible solutions for these. So now if these ranges are given, so what we do, first we have since a lower bound also and upper bound also. So first we change all these ranges to 0. And how do we do that? So if we want to make these 0, so from 1 we subtract 1 from all these sides. So next, so the condition that we get is basically 0 is less than equal to x1 minus 1 is less than equal to 5. Then we get 0. So first we are making the all the lower bounds 0. Okay. So we see that we'll have these conditions. 5 minus 1, which is 4. This is 4 plus 2. We are adding 2 in all these inequalities. So this is 6. Then we have third, we already have it to be 0. So we don't change this. And now we want to make this 3 0. So basically we are subtracting 3 from each of these. So we get that 0 is less than equal to x4 minus 3 is less than equal to 6. Now we call these are new variables. x1 minus 1 is y1, x2 minus 2 is y2, x3 is y3, and x4 minus 3 is y4. Now we are saying finding the integer solutions for x1 plus, we know the answer when the lower bound is 0 and we don't have any upper bound. So first we are making the lower bound 0. x3 number of integer solutions for this is same as calculating number of integer solutions when we have we condition this. So basically when we have these lower bounds, x1, we have these lower bound number of integer solutions. So we have these conditions on x1, x2 and x4. It is same as computing number of integer solutions of y1 plus y2 plus y3 plus y4. What is this? This is basically y1 is x1 minus 1, y2 is x2 plus 2, y3 is x3 and y4 is x4 minus 3. So this is x1 plus x2 plus x3 plus x4, which is just 18 minus 18 minus 4 plus 2, which is 18 minus 2, which is 16. So we are saying that finding in number of integer solutions for x1 plus x2 plus x3 equal to x4, with if we call these four conditions here, if we call these four conditions A, if all these conditions are A, so finding in number of integer solutions for this equation with A conditions is same as computing number of integer solutions for the equation y1 plus y2 plus y3 plus y4 is equal to 16 with these new conditions. Okay. What are the new conditions? That y1 is lying between 0 and 4, y2 is lying between 0 and 6, y3 is lying between 0 and 5, and y4 is lying between 0 and 6. So are you convinced up till now that if we want to find the integer solutions of this with condition A, it is same as finding number of integer solution of this equation with these new conditions, because we have just changed the variable. Is it fine till here?
Oh, yes, ma'am.
So now okay, now we want to find, so now we have changed this into this simpler problem when all the lower bounds are 0. So basically we know, so now now the next next hurdle is that we have these upper bound, that we have this restriction on y1, y2 and y3. So we take these restrictions. So if we remove these restrictions, like if we take a set to be where A1, where we are taking the integer solutions in case y1 is greater than 4, A2 is y1 is greater than 6, and A3 is y3 is greater than 5, and A4 is y4 is greater than 6. So by principle of inclusion and exclusion, we can say that number of integer solutions of y1 plus y2 plus y3 plus y4 equal to 16 with new conditions B is equal to total number of solutions without any restrictions minus the solutions coming in the cases A1 union A2 union A3 union A4. So this is the subtraction principle. So we want to find the number of solutions which are satisfying this criteria. So we are using the subtraction principle, which is that we are finding all the possible solution and we are removing all the bad solutions. And what are the bad solutions in our case? That is, a bad solution will be when y1 is greater than 4. Another bad solution case will be when y2 is greater than 6. Another bad solution when y3 is greater than 5 and y4 is greater than 6. So if any of these scenario will be happening, then then it is a bad case. So we have to subtract that because we are not required to count these cases. So if we want to find the solutions, so it is basically total number of solutions with this. So is it clear up till now why we are getting this?
Yes, ma'am, I understood, but
Yes.
this
Yeah.
A1 union, A2 union, A3 union.
A4. Yes. Yes.
Yes, ma'am.
You
Can
understand?
you tell me this step, ma'am? Total number of solutions without any restrictions minus.
Yeah. So I am saying, so we have to find the integer solutions of the equation y1 plus y2 plus y3 plus y4 is equal to 16, and we have these ranges for each y1, y2, y3, y4. So if we want to find this, what do we do is first we find, so we first we look at all the solutions. That is when we have no restrictions. That is this this scenario, total number of solutions without any restriction, is the solutions of equation y1 plus y2 plus y3 plus y4 is equal to 16 when the only condition is that yi are greater than 0. So this we know how to
Yes, ma'am.
calculate, right, from the previous.
Yes, ma'am.
Now, but what we do want to calculate, but we have these ranges this. So what we are doing, so we know these are the all the solutions. So we are removing the bad solutions. Bad solutions as in the solutions that we don't require. So solution that we are not required to count. So if we have, so among all these solutions, if we have any solution where y1 is greater than 4, we are not required to count that because range of y1 is between 0 and 4. So if your y1 is exceeding 4, we should subtract that solution, right? We should not count that solution. Is this fine? So if you have any solution
Yes, ma'am.
here
Yes, ma'am.
and
Understood.
y1 is greater than 4, we have to subtract that solution. So and a1 is basically calculating all the solutions of y1 plus y2 plus y3 plus y4 is equal to 16, where y2, y3, y4 are greater than equal to 0 and y1 is greater than 4. Okay.
Yes, ma'am.
So and so we have to subtract these solutions, right? Like whatever solution in among, so first first thing is we are calculating all the solutions which have no restrictions because we know how to calculate that. And now we are removing all the bad solutions from it. So first kind of bad solution is when y1 is exceeding the range, which is 4. Fine.
Yes, ma'am.
And similarly, we should not count any solution where y2 is exceeding 6. So a2 is counting those solutions, right? And a3 is counting the solution where y3 is exceeding 5, and a4 is counting solutions where y4 is exceeding 6.
Yes,
Therefore,
ma'am.
therefore we have to first count what all are the bad solutions. That is the solutions that we are not required to count. And then we so we remove them from the original number of solutions. Is this and hence we see that if we want to calculate the number of solutions for this equation with these conditions, we should first calculate the number of solutions without any restrictions and then remove all the bad solutions. Okay, is this fine?
Yes, ma'am.
So this is from like now what are the total number of solutions without any restrictions?
21.
Huh?
21, ma'am.
What? Sorry, I didn't hear. What?
21, ma'am.
One? What? One?
Ma'am?
What did you say? Sorry.
21, ma'am.
1T1. What is T? T1. Hello? 21. Okay,
21.
21. Okay. Why there are 21 solutions?
Ma'am, total number of solutions without any restrictions, ma'am. It will take 0 to 18, ma'am.
Okay. Hmm. Yes. Okay. Why are you like 0 to 18? What? Hmm. It won't be 20. Like you are saying the answer is 21.
No, ma'am. 21 minus 16, it will give 5, ma'am, with integer solutions, ma'am.
Hmm. Okay.
What I am telling, ma'am,
Okay.
they didn't give range means it
Hmm.
will come 21 solutions, ma'am.
Okay. Uh, okay. So if you so if you want to calculate these solutions without any restrictions, so basically you are calculating weak compositions of 16 with 4 parts, and this will be 16 plus k minus 1, which is k here is 4, 16 plus 3, choose 3. It should be 19, choose 3. Hello?
Yes, ma'am.
So this was like, so basically this was like we have 16. So we had 16 laddu. So if you want to, so if you want to find number of integer solutions, number of integer solutions of x1 plus x2 plus x3 plus x4 equal to 16, where xi are positive. So basically you are distributing 16 objects among 4 people, and this will be 16 plus 3, choose 3, because if you list down 16 objects, so you have 16 objects, and basically you have to put three you have to put three lines, because 4 people, a line is indicating that the first distribution for first student has stopped. Second line indicate that distribution for second student has stopped. So you see, you have 16 laddus and you have to place 3 lines. So you have 19 places and 3 options and 3. So you will have in total 19 places and 3 lines you have to put. So it will be 19 choose 3, 16, 19 choose 3. So without any restriction, without any restrictions, the total number of solutions were 19, choose 3. Is it fine? Like why without any restrictions it is the answer?
Yes, ma'am.
Okay. Yeah. And now next is you have to calculate this. You have to calculate the order of this set using principle of exclusion and inclusion and these techniques. Okay. Also, did you try assignment, like now, like later say, like for the last minutes we can discuss. So we have to submit assignment 2. So did you all submit assignment 2? Whoever
No,
is,
ma'am.
huh? Hmm?
No, ma'am.
Okay. What happened? Why didn't you submit?
Ma'am, I am enrolling this course, ma'am, but I not preparing, ma'am. We have exams, ma'am. That's why.
Okay. So when are your exams ending?
Next month, 10, ma'am.
Okay. Okay. Okay, but like if you are enrolling, like you should try doing the questions. Then only you'll benefit from the course. So what are you doing these days? So you only view lectures.
Yes. No, ma'am. I didn't view, ma'am. Uh, Today morning mail is coming, ma'am. That's why I attend this class, ma'am.
Okay. 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 So you haven't attained you haven't viewed any of these previous lectures from problem solving.
Mm,
Like
I will see only week one, ma'am. Week
okay.
one
Okay.
lectures, ma'am.
Okay. Okay. So do okay, so like since you have so do you have any doubts like in any like from like all over the course, any question there or any problem? Do you have any doubts?
No, ma'am. When I start preparing, then
Hmm.
I will ask, ma'am.
Okay, okay, yes. You can also put the questions on forums also. So
Okay, ma'am.
yeah, okay.
Which book is good for, ma'am? This combinatorics, ma'am.
Okay, combinatorics book so it is mentioned on the reference side, but also it is like so you can Richard Abrol I might be spelling it wrong, from like combinatorics. This is the book, and for the exact reference, like I might have spelled it wrong. So you can, for the exact reference, you can go to the course website. So this is the book we are. So it's like this.
Okay, ma'am.
Yeah. Okay then. Like I hope you understood something from today's lecture.
Yes, ma'am.
Okay. Yes. So like I'll end these sessions now then.
Okay.
Thank
Thank you, ma'am.